So before I dive back in, are there any questions I should entertain about where we've gotten to so far? Nothing obvious. Okay. So we have here a fit. And it's a reasonable fit, but it's a limited fit, right? All we've measured so far is the first coordination shell. And reasonable things happen. We got, as we talked about before lunch, we got, I think I started it. Yeah, I think we're good. So we got reasonable values, except for one that's a little bit low. We mostly got reasonable numbers for the parameters, and we got a reasonable fit. And that's fine and dandy, but there's obviously more to this material. So if this were a real research problem, then we would be compelled or interested in worrying about more of the data, because we have perfectly beautiful data with really big signal all the way out here. So if our interest is learning something about this material, we should make use of the data that's in front of us. So what we have here is fine. It's good. It's everything is great about it, but it's not the whole story. We really need to move on. So as we showed before lunch, we're going to need to include some number of these paths and then figure out how to deal with all the mechanics of the program to set up the parameters so that we can evaluate the EXAFS equation for all of the paths. Again, as I said before, I like to take small steps through a new research project. I find I get confused if I try and do too much at once. So the next thing I want to do is expand the scope of the fit to include this much of the data. So coming out to here. So that's about 3.8, where the blinky cursor is right now. It's about 3.8. So the next phase of analyzing these data is going to involve moving the fitting range out to 3.8. That is, to cover that much of the data. We know from what we saw before that to start to get a handle on this blob of peaks right here, we have to include quite a number of things. So the next small step I'm going to take is to just consider the single scatter rate. I'm not saying that the multiple scattering isn't important. I just want to take a small step so that we can understand how to include more paths and set up the parameters and do all the things that we need to do. So the next thing, after having set the fit range out to a larger value, the next step is to include these other paths. So I'm going to include these 4 multiple scattering paths by clicking this button, which takes away those parentheses that are the visual reminder that that's a path that is not being used in the actual evaluation of the fit. And now we have to start thinking about evaluating the EXAFS equation. And now we have a problem, or we appear to have a problem. So, first off, I want to use the values of the Fourier transform range and the fitting range to evaluate the number of independent points in the data. And the number of independent points in the data is about 15. We have 4 paths in the problem, and we have, for every path, 5 numbers that we have to evaluate. So, the total number of parameters, it would seem that the scope of the problem is that we need n paths times five parameters per path. So with n equals 4, which is what it currently is, 1, 2, 3, 4 are included in the fit. This is 4 times 5 equals 20. It would seem that we need to evaluate 20 numbers. But we have fewer than 16 independent points. So statistically speaking, it would seem that we've run into a disaster. It would seem as though we are numerically and statistically incapable of evaluating all of the green terms for all of the paths used in the fit. This isn't the end of the story. This isn't a disaster. We have ways of dealing with this. And the way that we deal with it is this. In the first fit that we did, where we fit just the first coordination shell, and we made these parameters, amp, E naught, del R, and SS, we used the parameters of the EXAFS equation as the parameters of the fit. That is how we evaluated the fit to the first coordination shell. In that fit, the parameters of the EXAFS equation were the parameters of the fit. In general, in an EXAFS analysis problem, the parameters of the EXAFS equation are written in terms of the parameters of the fit. Let me say that again. The parameters of the EXAFS equation are written in terms of the parameters of the fit. Now let me tell you what I mean by that. This is an intractable problem. 4 paths, 5 parameters per fit, 20 parameters that we have to somehow evaluate. Can't be done. We don't have that much information. However, these are not necessarily, or these 20 parameters are not necessarily all independent parameters. In fact, some of them are quite dependent, and some of them aren't even parameters at all. So in the case of working on the analysis of a crystal, we get to take advantage of an important trick. Right? Coordination numbers are not unknown to us. It's a crystal. We know that there are 6 sulfur atoms in the first shell. We know that there are 6 sulfur atoms in the second shell. We know that there are 2 sulfur atoms in the third shell. So we get to bring a lot of prior knowledge to this particular problem. Now, it's true that many of you have systems for which you go to the synchrotron, measure data, and what you want to determine is the coordination number. That is, many of you have problems for which the coordination number is the unknown, is the thing that you want to determine. And that's fine. And later on today and tomorrow, we're going to talk about how to solve those problems. But for this problem, for my teaching example, the coordination number is not an unknown. We have prior knowledge. It's a crystal. So the problem is not 4 times 5. The problem is 4 times 4, which is equal to 16. We don't have to determine n for each of those 4 paths because it's a crystal. Okay, that's swell. There's a couple more obvious things we can say about this. S0 squared, as I said this morning, is a parameter that tells you something about how the electrons in the system relax around the core hole that's left behind when the photoelectron is emitted from the atom. S0 squared is a parameter of the central atom. It is not a parameter of the scatterers. It's a parameter of the central atom. So whatever we use for S0 squared in the first path, we use the same parameter for S0 squared for all the paths. There's just one S0 squared parameter. So how is that implemented in the software? Well, now we get to start to see why we write the parameters here but we define the parameters up here. So we have defined this amp parameter to represent S0 squared in the EXAFS equation, but we want to use the same S0 squared for all of the paths that we include in the fit. So I'm going to go to the second path and type amp there also, and to the third path and type amp there also, and to the iron path and type amp there also. So now we start to see why there's this bizarre misdirection in the program where we use parameters down here, but we define them up here. So we've guessed an amp parameter, and we've used that parameter in each of the paths. So now, in the future, when we press the fit button again, the fit will go through its loop. It will, to obtain the best fit, it will keep updating the value of the amp parameter. And when it goes to evaluate the EXAFS equation for each path, it will use that same value as the value for S0 squared for every path. 4 paths, 1 parameter. So the problem is not 4 times 4. The problem is 1 plus 4 times 3, which is equal to 13. So the situation is getting better because we've thought about what the parameters mean. S0 squared is not an independent parameter for all the paths. There's just one S0 squared parameter in the fit. The same thing is true for delta E naught in this fit. As I said this morning, delta E naught is just this parameter that you'd use to line the theory up with the data, to put them on a common energy grid. All those paths come from the same theft calculation. They all need the same E naught parameter. E naught is an overall parameter of the theft run to line the theft run up with the energy grid of the data. So again, the E naught parameter that we've used in the first path is the same E naught parameter we need to use for every path. So, okay, I could at this point again go click and type and click and type, and that's a little tedious, so there's automation built in. I'm going to right-click right here and say export this to every path in this theft calculation, and now when I click down on the other ones, they have that E naught parameter. So we've improved the situation even a little bit more. We're now at 2 plus 4 times 2, which is equal to 10. So again, by thinking about the meanings of the parameters, we've reduced the scope of the problem dramatically. We've already cut the scope of the problem in half from 20 to 10, which is now below our number of independent points. So it's starting to look feasible that we can actually measure this thing. And we just thought about some simple principles. Okay, the next thing I want to talk about is delta R. So to do that, we need to go back and look at the crystal data again. So iron sulfide is a cubic crystal. All 3 axes are the same. Cubic crystals have a fairly high degree of symmetry. We get to make use of a nice trick in this problem. And this is the cubic crystal trick. This is not a generally useful trick, but for the problem that we have in front of us, we get to do this. The thing we get to recognize is that this is a cubic crystal. There's really only one parameter that determines where all the atoms are in the crystal. And that one parameter is the lattice constant. When we ran Thef on this crystal data, we either used the correct lattice constant, that is a lattice constant that's consistent with the EXAFS data that we measured, or our lattice constant is too big, or our lattice constant is too small. So, and all of the distances between atoms basically come down to exactly what the value of this number is. What I'm trying to say is that compared to the crystal data, what we measure in our sample for the EXAFS measurement, the lattice constant either needs to be bigger or smaller. The crystal either needs to expand isotropically compared to the crystal data or contract isotropically. So there's really only one overall parameter that determines all of the delta R's in the fit, just like there's only one parameter, that one, that determines all of the R's in the fit. Here's how that gets parameterized. So first off, I am just going to come here to the delta R parameter, and I'm going to change it to skip, which that means that it's still in the list, but it's not going to be used for any purpose in the fit. I basically just got rid of the del R parameter. We're not using that one anymore. Instead, what we're going to do, let me go back to the first path. What I'm going to do instead is this. And let me type it, and then we'll talk about it. Alpha times ref. Okay, there's a whole bunch of interesting things here. Oh, and we need to define the alpha parameter. So, alpha, and we'll define that to be 0. Okay. So, there's three interesting things, I suppose, that are going on here. One is a new parameter that we're calling alpha and that we're going to interpret somehow differently from the del R parameter that we had before. We'll get to that. Interesting thing number 2 is this word ref. Ref is a special word in Artemis and EXAFS. Ref always means the length of the path that is currently being evaluated. So for this path, let's try and get as many things as possible on the screen here. So for this path, the one that's currently displayed, ref is 2.2566. So when the EXAFS equation is evaluated for this path, if any of the expressions down here have the word ref in it, ref will be evaluated to be 2.2566. For path 2, if there's an expression with the word ref in it, ref will be evaluated as 3.44. And so on and so forth. Ref always means the length of the current path that was used in the FEF calculation. Ref stands for R effective. But that's really what I mean by that, is R effective, where what I mean by effective is the distance that was used in the FEF calculation. So, interesting thing number 3 is that we don't just have words in these boxes here. You can actually write down little math expressions. This is finally starting to peek into the whole point of Artemis and EXAFS. This ability to write interesting little math expressions to evaluate the parameters of the EXAFS equation in terms of the parameters of the fit is what lets us do really great things in the data analysis program. In that example that I showed you yesterday, where Scott Calvin fitted 3 edges and all kinds of anti-site disorder and all kinds of oxygen vacancies and the effect of nanoparticle truncation effects, the reason he was able to put so much information into the fit and extract so much information from the data is because we can write down these interesting math expressions that describe the physics, the real science of what's going on in the problem. In this case, the real science of what's going on in the problem is that it's a cubic crystal, and the thing expands isotropically relative to the crystal data, or it contracts isotropically. Alpha times ref does that, right? If we have alpha times ref, and I need to, at this point, right-click here and say export to every path in the FEF calculation. and now they all say alpha times ref. So if alpha evaluates to some number, the delta r of the first path will be of a certain size. The delta r of the second path will be a little bit larger, just like you would expect for an isotropic expansion or contraction. And for successively longer paths, delta r will be successively longer. Alpha times ref is an isotropic expansion of delta r in the EXAFS equation. Does that make sense for a cubic crystal? People are willing to buy that? So we have alpha times ref as our parameter. As we'll see in a second, alpha will evaluate to some value, and when we go and look at what delta r is, the delta r's will be monotonically increasing or monotonically decreasing path by path. We'll see that in a second. Okay, so because this is a cubic crystal, we get all of our delta r's from a single parameter. So we've improved the situation here yet again. 3 plus 4 times equals 7. So we've now reduced the scope of the problem from the apparently intractable 20 all the way down to needing only 7 parameters to fit the data out to 3.8 using 4 single scattering paths. So finally, we need to talk about sigma squared. Sigma squared is the tough one, and I don't really have a cute trick to use for sigma squared. Right? I was able to talk away all of the other parameters by thinking about what I know about the material. And I can't really do that for sigma squared. So, right, the nearest neighbor will have some sigma squared, and in fact we've measured that once already. Right? The nearest neighbor had this value for sigma squared. Sort of the one thing that's probably true is that things that are farther away will have a somewhat larger sigma squared. That is, the mean square variation in a longer bond length is likely to be bigger than the mean square variation in a shorter bond length, except it really has to do with how the atoms are all fastened together. So often you see a situation where the nearest neighbor is quite stiffly bound, strongly bound, and therefore has a relatively small sigma squared, but a more distant neighbor might be part of some other structural unit in the material, and the relationship between those two things might be a lot floppier. So sometimes it happens that nearby things have relatively small sigma squares, and farther away things have much larger sigma squares, much larger in a way that isn't necessarily easily related to the value of ref. It's just hard to know. I don't have any clever trick up my sleeve to relate the sigma squares of these 4 single scattering paths. So because I am without a good trick, I am going to do the simplest thing I can think of, which is to simply allow each of the single scattering paths to have its own sigma squared. So we've done a really good job of constraining S naught squared, E naught, and delta R path to path, but I don't have a good way of constraining the sigma squared. So I'm just going to make 4 sigma squared parameters, and we're going to end up with 7 parameters in the fit. So for the second sulfur path, that's going to be SS2. For the third sulfur path, I'm going to call it SS3. And for the iron one, I'm going to call it SSFE. So, a moment to talk about nomenclature. None of these words that I've selected, with the exception of ref, which has a special meaning, none of the rest of these terms have any particular meaning. That is, you get to choose the names of your parameters. I chose the name amp, but it doesn't have to be amp. I can call it something else, right? I could call it I don't know, Harold. That's a perfectly fine name for a parameter. The problem with Harold as a name for a parameter is that it doesn't really suggest what it's doing in the fit. So I like to choose my names so that They're suggestive of what's going on in the fit, but the point is that I get to choose the name of the parameter. What's even more relevant is some of you in the audience are not native English speakers, and you're not obliged to choose English language words for the names of your parameters, although you do have to stick with ASCII characters. You can't use an assert or a Japanese character in the name of your parameter and expect the software to be happy about that. But otherwise, you can pretty much name these parameters whatever you want. So I need to define my SS2, SS3, SSFE, and in here, SS, SS2, SS3, those are the sulfur ones, incremented by shell, and SSFE is obviously the sigma squared for the iron scatterer. So those are sensible names for me. 3, 0.003, 0.003, carriage return, and now we're good to go. So now we're about ready to hit the fit button. We're about ready to hit this guy. We've set the fitting range to cover the first big peak and that next blob of peaks. We've included our first 4 single scattering atoms. We have defined our 7 parameters up here. We've used them all in a sensible way down here. So yeah, I think we're ready to hit the green fit button. And here's our fit. Not bad. Not perfect, but not bad. Here's a little problem, which you can see in the real part. A little bit of a misfit there. A little bit of a misfit there. It's pretty good, but it's not perfect. If we look at the values of the parameters, things by and large actually make pretty good sense. The S0 squared parameter got a hair better than it was last time. If you recall, the last time it was, I think, 0.66, and now it's 0.69. It's still a little smaller than I would expect, but, looky there. E naught is a reasonable value and with a reasonably sized error bar. Alpha is a positive number but consistent with 0. And let's go look and see how that propagated through the whole problem. If we go down here and look at our 4 single scattering paths, we see that with that value of alpha multiplied in each case by ref, that we got delta R, so our refs are monotonically increasing, and our delta Rs are therefore monotonically increasing because of the behavior of this isotropic expansion coefficient. So our isotropic expansion coefficient worked the way we would expect an isotropic expansion coefficient to work. So that's all sensible. And we got about the same value for sigma squared, the first sigma squared. The second sigma squared is bigger, kind of like we expected. The iron sigma squared is bigger yet, kind of like we'd expect. This is a bit strange. The sigma squared for the third path is kind of oddly small. Doesn't really make a lot of sense to me that whatever is holding together the iron atom and the third coordination sulfur, whatever chemistry are holding those 2 atoms together, it doesn't make a lot of sense to me that they're held together more tightly than the thing that the iron actually has a chemical bond with. Doesn't make sense that this number should be smaller than that number. But at least it's not negative. Well, it is negative. It's consistent with a negative number. SS3 is not actually positive definite, and it's oddly small. So that's a problem we're going to need to think about at some point in the investigation of this fit. It's a problem with the fit. That is a number that we could not easily publish because it's not a number that we could not easily defend. So that's a problem. A little bit more about the mechanics of the program. You have right? So suppose I go and I make this plot over here using click. What is going on? There we go. I think there's some weird interaction between the desktop beamer thing. So, okay, so I made a new plot, and I'd like to go back and see that plot that came up after the fit, the thing with the real part and the magnitude. That is what I call an RMR plot. That's this one here. So that recovers this picture, and it respects these buttons over here. Because the fit button is ticked, the fit got plotted for both parts, and because the window button is ticked, the window got plotted for the first part of it. Here's a plot that shows you the data and the fit with each k-weight, but scaled so that they all show up on, at the same size. So this is the k-weight of 2 Fourier transform. This is the k-weight of 1 Fourier transform, but blown up a bit so that it plots in the same size. And this is the k-weight of 3 Fourier transform, scrunched down so that it all plots together. And the thing that's nice about this is it lets you visualize, sort of all the different ways you might do the k-weighting. You can visualize them all at once. That sometimes is useful for giving you a hint about what might be going on in the data. There is the same kind of plot, but in k, and there's the fit in chi of k with the 3 different k-weights. These are just different visualization tools, different ways of looking at the data. The last one I want to show you is this one, the RK plot, which benefits a little bit by making the window a bit taller. And it's just a combination of the currently selected value of k-weight. So whatever k-weight is selected up here, that value shown in k, magnitude of r, and real part of r, all at the same time. This is actually how I make plots for data in my publications. This is my favorite plot of data for a publication, is k on top, r like this on the bottom. I find it the most compact way of presenting as much information about the fit as possible. So I highly recommend this. I like it. All right. Our fit, as I said, ain't perfect. We're missing some stuff. Here, we're missing some stuff. Here, it's just not quite perfect. And before we get into fixing that, I want to make one more interesting plot for you. So unmark all, mark included, and that put the little tick mark next to the 4 paths that we included in the fit, and transfer marked, because now I want to make this plot, which is the data and the 4 things that we included in the fit. And we see now with sigma squared and all of the other parameters applied to the paths, we see how each path relates to the data and how they all add up to make the data. This is a little bit of a busy plot, so a thing that I often like to do is click on the stack tab, do a stacked plot, and we'll use a value, I think 0.25 will be a good value here. And that makes a plot that looks like this. And this, I like this. This it sort of uncovers the individual paths in a way that it doesn't make a big visual mess on the plot, but you can still easily see how paths are related to one another. So this is pretty useful. I mean, you again get to see how each part of the theory calculation contributes to the analysis of the data. It's always useful to stop and look at these things and see how things are going. All right. The 2 largest multiple scattering paths that we've seen so far were these 2. The one that hits a first coordination shell sulfur, second encloses, and the one that hits first coordination sulfur, iron, encloses. Those are the two biggest ones. So let's start by including those. Somehow they didn't get, I guess I never pushed these out, so let me give them the correct value of amp. So both of these single scattering paths, so we've now made the problem worse in the sense, the original problem would appear worse in the sense that this is 6, so all of these become 6, this becomes 30, this becomes 24, 19, 6 times 2, 14, and 11. But we're not going to really change this number, right? Our total number of independent points don't get any bigger, but it would seem that we have, it would seem at the beginning that our problem got vastly worse by adding too many paths. But of course it's not vastly worse because there's just one S0 squared, there's just one E naught. The isotropic expansion trick works for a multiple scattering path because it works for every leg of every kind of path in the problem. It's a cubic material and it's an isotropic expansion. So this alpha times rep thing is going to work just fine for these multiple scattering paths. The thing I'm not too sure about, or the thing that we need to think about, is sigma squared. So the simplest thing we could do is simply give each of these paths their own independent sigma squared, which is fine, I guess, but it comes at a price. It comes at the price of introducing a couple more parameters to the fit. In the case of this path that wasn't very big, we'll be adding an entirely new parameter to the fit for a path that's not actually all that tall, that doesn't really contribute that much spectral weight to the fit. So that might be a little bit troubling. It's concerning because we might be adding a parameter to the fit, but not adding a robust, well-determined parameter to the fit. But you kind of have this sense that we shouldn't even have to add any more parameters at all. And here's the reason why. So we're kind of done with this point, so I'm going to erase that. So we have the iron atom and the sulfur 1 atom, and somewhere else is the sulfur 2 atom. And I'm not really certain what kind of triangle they make. We'd have to go look at the coordinates. You could look at these numbers and figure out quite exactly how they're supposed to be laid out. But my point is that a path that does that, a certain resemblance to this single scattering path and this single scattering path. That is, the mean square deviation in this path, in this leg of the path, must be somehow related to the mean square deviation in the single scattering path that hits the first shell sulfur atom. Similarly, the mean square deviation in this leg of the path must be somehow related to the mean square deviation in the single scattering path that hits this sulfur atom. So, in some hand-wavy way, the sigma squared of the S1, S2 path must somehow be related to something, somehow be related to this. I don't know if, what I mean by this is not a near equality. What I mean is that there must be some relationship between the sigma squared for this path and these two sigma squares with a factor of half because it's half as long, or something like that. But then there's this bit that we don't really know what to do with because we don't have a single scattering path in the fit, obviously, that relates to squared associated with this leg. I mean, we don't have a piece like that in the fit. But that's sort of the unknown part, but it's a small part of the fit. So I'm troubled introducing a whole new parameter, but I'm troubled because I don't quite know the relationship. So now I'm going to assert something. We'll put it into the fit, we'll do it, see what happens, and talk about it after the fit is done. So what I'm going to assert is that I can approximate what's going on in that path. I'll get the sigma squared for that path more or less right by doing something like let's make it a little bit simpler than that. Something like this. So I'm going to just assert that if I add up the sigma squared for this single scattering path, the sigma squared for this single scattering path, that the sums will be approximately equal to the sigma squared that you would get for this triangle. Certainly not equal to. That is certainly not correct. I'm kind of making something up here because I need to have something to put in this box. And we'll come back to it. We'll discuss the validity of the approximation in a second. This we actually know a bit more about because now, instead of being S2 here, this is FE. So we have one leg that is FES1 and another leg that is FES1. So these two legs together should have a mean square variation that is the FES1 sigma squared. And this is half of the iron-iron path. So a slightly more defensible approximation can be had for this one. SSFE divided by 2. Again, that's just a hand-wavy approximation. But here's the great advantage of having done those two hand-wavy approximations. I've added all of the contributions from these two multiple scattering paths without introducing a single new parameter to the fit. I've added more information to the fit, more stuff to the fit, but I'm not requiring the fit to determine any more floating parameters. Let's see how this goes. Well, I actually think this is an improvement. Adding the multiple scattering paths seems to have had a significant impact. I think things are a little bit cleaner here. We still have a little bit of misfit, and we're missing something over here. But on the whole, I think this is an improvement over the last fit. That is, the contribution of the multiple scattering paths appears to have been important. Let us add those two things. We'll say transfer marked. We're going to do that stacked plot again. And here's what we've got. So the bottom two, the yellow one that's hard to see and the blue one that's also hard to see, are the contributions from the multiple scattering paths. But look, this is a significant peak. It's as big as the peak from the third sulfur shell. The yellow one isn't so big, but it has some spectral weight that sort of extends through this whole region. So these two paths really do seem to be part of the fit. How do these things add up? Well, they have some kind of phase relationship. So if we make the plot this way, and the stacking isn't enough, let's change that number. You see that we've got these interesting phase relationships between everything. So the effect of having this multiple scattering path is to take away some of the weight from, some of the spectral weight from the iron scatterer, which is part of what helps make the red line look like the blue line in this region. So Right, because all these things add up with this complicated phase relationship, you have to put enough stuff in the fit to really match the data. And these data are telling us that to understand them, we have to start including some of these multiple scattering paths. It's part of the problem. And to get this, we have to think about the multiple scattering paths. Okay, so that's what the fit looks like. Of course, it's not enough to just say that. What happened? It's not enough to just say that. It's not enough to just say that the red line looks like the blue line. We have to evaluate the parameters, and we see a consistent, if small, march towards reasonability in the amplitude parameter. It's a bit bigger. It's starting to get into the range that we expect. E naught hasn't really changed throughout this whole exercise. Alpha is a small number and still consistent with 0. Sigma square, that's a little bit bigger than it was before. That's a little bit smaller than it was before. The one for SS3 is still a little strange. It's still not quite a sensible number, and it's still not even positive definite because the error bar is so large. So this is still a bit small. This is still problematic. But everything came out sort of reasonably. If we look down and see how all of our math expressions panned out, we see that, we have still have reasonable values for the sigma squares for these paths. But, we need to think again about these approximations that we made. We made this one and the other one that are they were hand-wavy approximations. I will assert, but leave as an exercise for all of you to try out when you start doing some fits. I will assert that it is better to include the multiple scattering paths somehow than it is to not include them. I think we already saw that. I mean, we saw an improvement to the fit when I added those two paths. And we saw in this plot why including them is important. It's because they contribute significantly and out of phase to the big contributor in this region. So it's important to have the blue one so that the blue and the pink together do the right thing. So it's better to have multiple scattering paths than to leave them out of the fit. And the part I'm going to assert but not demonstrate right now is that it's better to approximate their sigma squares in terms of parameters that you already have in the fit by using math expressions than it is to make up entirely new parameters. And that's easily tested. The sense in which it's easily tested is you could just, for this path, erase this, make a new parameter, define it up in the parameters page, and run the fit and see what happens. You'll get values out. You'll get statistical analysis that lets you compare the fits. And in general, you'll find that adding new parameters for these triangular multiple scattering paths is a worse idea than approximating their values on the basis of things you already have in the fit. But I'm going to leave that as an exercise for you. I'm going to do two more things on this before wrapping it up. We still have plot, and I wanted to plot the magnitude there. We still have quite a bit of misfit out in this part of the fit, and I'd like to address that. I'd like to see if we can solve that problem before calling it quits. So my first thought for what that might be is this thing. This is the fourth coordination sulfur atom. If we go back and look at the FEF input file, we see that there's this cluster of 6 sulfur atoms out here a little bit beyond the iron atom. That's what that path is. Amp. So amp E naught alpha times ref, and we have, for this one, we don't have anything in the fit that works for it. This is a new single scattering path, so we need a new sigma squared parameter, SS4, and we have to define it. SS4, 0.003, and let's plot it. Let me clean some things off the screen. So we'll put the log away. We'll put that away. We'll put that away. And here's. Let me undo the stacking thing. Remake the plot. So here is, without having done the fit, so we don't actually have a value for SS4 yet because we haven't run the fit yet. But here is where the fourth shell atom contributes relative to the data. Its peak is somewhere out beyond the range that we have right now, and it's somehow contributing to these small things down here. So I want to expand the fitting range out to about 4.2 and try the fit again. So 4.2 will now do in this range, so that we're including the fourth shell sulfur atom. And let's see what happens. Well, that looks a lot like it did before. And the reason it looks a lot like it did before is that the fit really didn't like having that sulfur atom there. It made the sigma squared enormous. That has the effect of making the contribution from that path really very tiny. In fact, when we plot it, you can't even see it because it's written over the black line at the bottom of the screen. So that enormous value of sigma squared served the purpose of kicking the fourth shell sulfur atom out of the fit. So how can we understand that physically? Well, whatever the structural units are in iron sulfide, they're relatively rigid. Things are relatively rigidly connected together out to a certain point. But beyond that, they're not very rigidly connected. I suspect that just from thermal motion, the fourth shell sulfur atom is moving so much relative to the iron atom at the center that the sigma squared is really large. We just don't see it in the data. And the way that the fitting program gets rid of a path is by making its sigma squared really big. So I'm just going to jump right to the answer. It turns out that that is not the thing that you see to make up for the last little bit of the fit. It turns out that what we need to include are these three paths down here. Let me drag them and drop them over, and then I will explain to you what those three paths are. So those three paths are this. We have an iron atom in this thing in the middle of a sulfur octahedron, where there's another one coming out here and another one going into the board. Those three paths are, let me just get rid of these two for this purpose. Those three paths are that, and that, right? So one of them, this one here, it turns out, is the path where the photoelectron propagates out, scatters off the sulfur atom, propagates back without scattering off the iron atom, and scatters off the sulfur atom on the other side, and then closes the loop. The next one, this one, does the same thing, except it also scatters in the middle off the iron atom. The last one rattles back and forth between the iron and sulfur atom. It goes boing, 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 boing. So it turns out that these three paths together are what we need to finish off the fit. So let me do a little bit of typing really quickly. So we needed amp and E naught. In fact, this typing is going to drive me crazy. So let me unmark all, mark the three paths I just put in. I'm going to export path parameters to each marked path. So now things like this one and this one are unchanged, but I just pushed all of the parameters from this path to all three of these. So they each needed amp, they each needed E naught, they each needed ref, and we need to figure out what sigma squared should be. These collinear arrangements of three atoms, it's very easy to figure out what sigma squared should be. These two, if this path gives a value of sigma squared, this path, these two are 2 times sigma squared, and this one is 4 times sigma squared. There's a handout that goes along with this talk. It's one of the things that I pointed you to download before, and it's one of the things that's on my GitHub site. And I explain, or I give the reference to the derivation of 2 times sigma squared and 4 times sigma squared. It's really quite simple, and you can probably figure it out just by thinking about it or looking at, doing a little bit of math in the back of the envelope. Or you can go check out the reference in the PDF file that is like the follow-up to this presentation. So those numbers are knowable. This one is times 2. This one is times 2. This one is times 4. I've added those 3 multiple scattering paths. I have included no additional parameters in the fit. Even the sigma squared parameters are determined from things I already have in the fit. I hit the big fit button, and voila, there is my final fit to iron sulfide. So now this is sort of unimpeachable. You'd have no problem publishing this fit. That looks great. How do the numbers look? Why does it do that? So this number got a little bit smaller again. Drat. That's still reasonable. This actually got a little bit better in the sense that it's better determined. The error bar is smaller now that we've included more paths in the fit and a little bit more data range. SS2, and SSFE are all still sort of the values that you would expect with reasonable error bars. SS3 is still problematic. SS4 is still really huge and is basically kicked out of the fit. And the reason that we were able to fit the last bit of the data is because we included those, it turns out, important single scattering paths. So with a few exceptions, I'm done with this problem, and I'm about ready to publish. Let me just show one more thing, and then I'm going to call it quits for the moment. So let me... is that happening? Yeah, there we go. Wow. You keep asking me that. So let's go back to my GitHub page. So one of the presentations that I prepared, this is really just a supplement to this demo. This isn't really a presentation, but it's a PDF file, and you can grab it and look at it. And let me just point out a few things that I have in here. And I clicked on the wrong file, so let me go back and click on the correct file. Works better that way. Click. So here are some references that discuss S0 squared and the determination of amplitude. In these two slides, I talk about what's going on with the sigma squared of the third sulfur scatterer. Here I talk about the constraints on sigma squared for all the multiple scattering paths and give you a reference to this talk, which explains that thing over there. On this page, we talk a little bit more about the fourth shell sulfur atom. Some more interesting information. Here is a careful derivation of the alpha times ref parameterization, in case you never really believed that in the first place. Some more discussion of delta R, some discussion of correlations, and something else that I haven't talked about yet, but we'll talk about later. And so what I recommend is that you grab a copy of that talk and have it with you if you go and try and reproduce all of this work. I'd recommend having a copy of that talk because it talks about several of the points that I haven't gotten to because I had to talk about all the other things. So that's how you use Artemis. I don't really expect any of you who are coming to this for the first time to walk away from this talk as any kind of expert or even necessarily like getting the whole point of Artemis, but it should be enough to get you started. If you plan to do EXAFS analysis as part of your work, it's a really good idea to spend some time up front working on simple problems so that you can learn the mechanics of the program and learn how to use the program before you dive into a difficult research problem. Right, this is a teaching example. There are some things that are simple and well known about this, but if you can understand all the mechanics of doing the teaching example, you'll be much better prepared to dive into your real research problem. Using Artemis is big and hard. EXAFS fitting is big and hard. There's sort of no way around that. But the beauty of Artemis is that it gives you all the tools to do amazing things with your data. So that's it for now. I need to take a break for a few minutes. Any questions? I guess, are there any immediate questions? If nobody has any questions about how you fit EXAFS data, then we might as well just tack it in now.
S0 squared, S whatever it is squared.
Yep.
That, if I've got this right, that's a property of the absorbing atom.
Yes.
So should that then not be the same? You know, I mainly work with palladium sage, so should that be essentially the same for everything I ever do where palladium is my absorber?
More or less. There's two problems with that. One is that, so imagine back to the single scattering problem where we have just one path and we're trying to evaluate this equation. If you don't know n, if n is something you're trying to get out of the data, you can't measure these two numbers independently because they're multiplied by each other. They are 100% correlated. I'm sorry, they're minus 100% correlated. Right? If this is supposed to be 12 and this is supposed to be 0.9, you get the exact same fit if this is 120 and this is 0.09. These are completely correlated. So there are some problems for which you can't measure them independently, and so what people often do is exploit what you said, and there's a phrase in the EXAFS literature for what you just said. It's called chemical transferability, where we say that S0 squared is the same for everything of the same atom. So what you might do in that case is measure a palladium foil for which you know n, get S0 squared as something you evaluate, and use that in your subsequent fits for the value of S0 squared. That is a common thing to do. But the caveat there is that if you have any inhomogeneities in your sample, if you have any nonlinearities in the detectors at your beamline, or any other like weird stuff going on in the measurement, all of the weird stuff that goes on in the measurement tends to affect the amplitude. So there's really sort of a hidden additional term in the EXAFS equation that is problems in the measurement. And if A is not equal to 1, that is, if you had problems in the measurement, then you're going to have trouble measuring or using your chemical transferability or whatever. So the short answer to your question is yes. The long answer is yes, but. You're welcome.
Just the range of R that we include in the fit when we stack the spectrum to see that shell actually involved in the spectra, and then we shoot to fit, and it's not actually cover the tail. So we like that. I saw you select the 4.2 instead of 4.5 that cover all the tails of that
Right.
spectrum. So
That would
actually,
probably be better.
So
Yeah.
we actually shoot the range that is actually not covered all the tails, or
So that's a little bit of a difficult question to answer completely generally, because as you saw from the stacked plot, everything overlaps with everything else, and everything has long tails. And there's whatever stuff is out here actually bleeds back a little bit. So as long as you're not including all the stuff out here, it's hard to know what exactly the right point is. And if you're not including all of this stuff, it's hard to argue that the fit should be there or there or there. Right? You can't really make a good argument about that. So I tend not to worry about that too much. I just sort of do what I did. I see where most of the weight from the paths is, and make sure most of the weight of all of the paths is covered by the window. But I don't really worry very much about whether it's 4.2 or 4.3. It can't matter. I mean, if the fit is that sensitive, then you have some instability in the fitting model. And you should probably be including whatever stuff is out here